Okay, since it's 3 p.m. already, I'll get started with today's class. So hopefully others will watch this video later on. So welcome to the week 11 class on optimization methods for civil engineering. So in this week's TA session, I'll be mostly discussing on differential evolution, then the MATLAB, introduction to MATLAB, and then solving some of the classical optimization problems using MATLAB. So I won't be going into much details of differential evolution or the multi-objective genetic algorithms, as that will be discussed more in detail in next week's TA session. So in this class I'll be covering R coding for differential evolution, and then we'll go into MATLAB and solve some of the classical optimization problems, and also we'll look at some of the basics of MATLAB, and also the assignment problems related to that. I'll be solving some of the sample problems. So that's the objective of today. So as like last week, I don't have any slides as such because I'll be solving. Okay, so we have one person joining, so I'll add him. Hi Manohar. So I'll get started with today's class. So today what I'm planning to do, I'll be discussing differential evolution using R briefly. Then I'll go into the introduction to MATLAB and then solve some of the classical optimization problems using MATLAB. And finally, we'll look at some of the assignment problems, and related to that, I'll be solving some of those problems. I don't have slides as like last week. I'll be directly solving those problems in R and MATLAB. And I won't be discussing much of this multi-objective genetic algorithm this week because that's more of a focus of next week, and those problems NSGA2 and those things will be taken up in the next week's TA session using R and MATLAB. Okay, so I'll get started. So I have shared my screen already, so I think that's visible. Now I'll go into R and solve the differential evolution problems that you have already seen in the class. So just to briefly talk about this problem. So I hope my R studio is visible. So for this differential evolution, I think you have already gone through this lectures. I think these lectures were posted a bit late this week, but if you haven't gone through it, that's okay, because to understand its code, you need just one line, and you already know the command, so that's not a problem. So here first you have to install this package DEoptim in order to solve this problem using differential evolution. So as I have already installed it, I won't be doing it again. And then you will import this library DEoptim by running this. So that I have done already. So let's check whether I have imported it correctly. Yeah, so I see the tick mark here, and this DEoptim is activated now. So let's now look at the function that I am optimizing. This function you have already seen before. It's x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. So I've written the function. Then the sequence function gives you those intervals. So you'll plot these points between 0 and 5, and with those intervals of 0.1 along both x1 and x2 directions. So let me run this line. Then you have this outer function, and these things you have already seen. So first you can do some sort of a surface plot that will give something like this, and you can also do contour plots with number of levels equals 100, and that will make this function look like this. So now in order to use this DEoptim function directly, what I have to do, I have to express my function in terms of this vector x. So here I have it defined using scalars, and that was useful to plot those functions, but you can directly use vectors as well. So since I have to use vectors anyway after this, so I'll again define this function fn using the vector notation, and that I have done. And now this DEoptim function, what it does is it solves this problem, this optimization problem using differential evolution So the technique, it's similar to genetic algorithms. It's also a population based algorithm, but here the mutation is slightly different from what you have seen in genetic algorithms. I think you will go through the lectures. When you go through the lectures, you'll understand it a little bit more. And then you have some recombination being done, and those things are there in differential evolution. So anyway, this portion will again be discussed next week in detail, so I'm not going into that thoroughly right now. So just understand that you can just write this one line of function, this function call if you make. So, and then what you are throwing here is the function itself that you are optimizing. These are your lower limit of your x1 and x2 variables, lower bounds, you can say that as well. And these are your upper bounds of your x1 and x2 variable. So when you run this, you are storing the result in this variable res. So let's run this line. So it ran 200 iterations, and the function, that value, it's 0, and what you got is the solution point you got is as 3 and 2. So we have seen before, this was one of the solutions of this function. Okay, I think another person has joined. Okay, so if you see this summary now, yeah, it tells you that the number of times this function was evaluated was 402, and you had 200 generations. This best value is the objective function value, and these best member is the solution point that you have. And you can also plot this, and this is for parameter 1 like x1, and it converged after a few iterations to 3, and also this x2 also converged to 2 after a few iterations. So it's the person joined, I guess. Yeah. Okay, so that's all about this differential evolution. So the theory part, I think you need to go through the lectures, then you'll be able to understand it better. Anyway, I'll be discussing it again in next week's class. And this is all that you need to know for now, is that you just write this one line of function and it will solve it for you. So there are other parameters that you kind of define here. So if you write help, then you go to this d-optim. So now it gives you all the arguments that you can pass through this d-optim function. So I have only used function expression, then the lower bounds and upper bounds. You can also use some control parameters. So I'm not going into the details of it, but in the next example you will see some of it. Okay, so let's get into the next example for this differential evolution part. So again, as before, it's pretty similar. It's just the function that I am using, it's different. It's I think sir has already covered this in the class, but I'm just going through it for the sake of completeness. Okay, so let's again, you can import that library d-optim, so that's fine. The function expression is something different here. Now it's 10 plus x1 square minus 5x1 x2 plus 9x2 square plus x2. And then similarly, you can do some sort of a contour plots. It will look like this. And again, you represent it using vectors. And then you can run this, again, this d-optim function, and you can pass that function value, then the lower bounds of your x1 and x2 variables, which is minus 5 and minus 5 here. And the upper bounds are 5 for those variables. And here, this is the control parameter. This is the extra thing that I am using here. So this d-optim.control, so this first term that you pass here, the first argument is the population size. So this is the population size of 80 that you are fixing. Itermax is the maximum number of iterations that you will perform. So here I am fixing it to 400. Earlier, I think it was by default some 200 iterations in the previous problem that we have seen. This f value, I think if you have gone through the lectures, then you will understand it's kind of related to the mutation that you do. It's f times the difference of the directions of the other 2 points that you kind of randomly generate. So you can set it between 0 and 1, also you can set it between 0 and 2, so not a problem. So this here is again related to the recombination step. So this is the probability of recombination. So typically it is being set as 0 between 0.5 and 0.7. So here it has been set to 0.7. So I can use these parameters and I can run this. So when I run, it will run for 400 iterations. And I think you have seen this problem before in one of the problems that I solved last week as well. So the objective function value at optimality will be 9.91, and these are your optimal solution points. So if I write the summary, so this gives you the summary, and it is after 400 generations that you have set here. And then you can plot as well. So this plot will give you the convergence of those parameters. And you can set different values here maybe, and you can try it out whether you are getting to optimality or not. So this f you can probably select as 1, as 0.5, so you can play around with these parameters. So here also I'm getting very close to the optimal solution itself, so that's not a problem. Yeah, so you can, even if you use a population size of 10, so it gives you the optimal solution here. Okay, so that's all about I wanted to discuss about this topic, which is differential evolution. So I think more of this will be discussed in next week's class, with maybe with some problems in R or MATLAB as well. So let's get into MATLAB now, because that was the main focus of this week's content. So I'll close RStudio for now, but before that, any doubts or anything that you have from the first two lectures of this week, multi-objective genetic algorithm or differential evolution, you can ask me now. Otherwise, I'll move on to MATLAB and other things. Yeah, go ahead. Yeah. Yeah. Yes, that's correct. Yeah. Let me check. Actually, I forgot the expression. I'll just check and tell you. So just a minute. Okay. So I think it was on one of the slides. Yeah. Yes. Yeah. So yeah. So I think the slide is kind of visible here. So yeah. So what you do, you generate a random number, then this CP, if the random number is less than equals to CP, so suppose you have taken it as 0.7, then you are taking this V1, so this V was the donor vector itself, and for the if your random number that you generate is greater than 0.7, so it's like 30% of the time you are taking it from the target. So the X was, I think, the target here. Yeah, you can think like that as well. It's the probability that you are selecting. So that's the probability of, yeah, exactly. Yeah. Yeah, so yeah, target vector is XNG. So that's fine, I guess. Yeah. Okay, so any more doubts that you have? Otherwise, I'll move on to MATLAB. Okay, so let's get into MATLAB then. So I'll close RStudio for now. All right, so first I'll discuss pretty basics that have been already covered in the class. Then I'll get into the classical optimization problems that were kind of discussed in the class, and also the kind of problem that you will get in your assignment. Even though the codes and everything have been given in the assignment, but let's discuss everything in detail here itself. So first of all, it's installing MATLAB. So that can be a challenge itself. So you can either use online platform like online tool to directly use it in online, but I would recommend you to if you can download it and install it in your PC, that will be helpful. And like many institutes have this academic licenses available to them, so you just need to log in using your institute email ID, and that should be fine, and you will be able to download and install MATLAB. Even if you don't have, even if your institute don't have those kind of access, I think there is a way of using MATLAB for 1 month trial version for free. So I think even if you install it now, so that will be fine in your exams also. That will be in this month itself, so that will be sufficient. Did Manohar, did you install MATLAB, or did you have MATLAB from before, or like did you try it out? Uh, Sorry, I couldn't hear you probably. Mhm. Yeah. So it is already there for you. Okay. So, and you kind of familiar with the steps of MATLAB, right? You have used it before. Oh, then it's great. So I'll go through everything, because since someone might be hearing this recording later on, so that will be helpful for them if they are new to MATLAB. So anyway, I used MATLAB, I think some 4 years back. Even I was getting just a refresher when I was doing this assignments and all this week. So so I installed MATLAB, the academic version, here in my laptop, and it's pretty simple first few things. So let me go through everything. So I think these things have already been discussed in the class. So the CLC command is for clearing this command window. Clear variables is like clearing all the variables from your workspace. Then you can store, say, values a equals to 20 here. So in R you can use that left arrow kind of notation, as well as equals to, but here you have to use equal to itself. Then suppose this semicolon, it kinds of suppresses that line, so that line will be executed but won't be like getting reflected in the command window. So let's do this. I'll run this line by line. So you can select everything, and you can just run that portion by typing F9 from your keyboard. So if you do that first, since I don't have anything, so that's fine. So suppose I run this line, and then this a is 20 here, but if I just remove this semicolon from here, let's see what happens. So earlier, yeah, it ran this line, and let's do this. Yeah, here it kind of gives you some sort of an answer. It's like a equals to 20 separately if you don't use that suppressor semicolon. So it's pretty simple. So now suppose you have a equals to 20, b equals to 15, then simple addition should give you 35. So let's run the entire thing together. Then yeah, it has given c equals to 35 here. You can check from workspace as well. Then defining vectors. So this vectors you can define either by separating every element by commas, or you can separate everything by a space. So that's either way is fine. So let's run this portion. So now you have your x and y is stored like this. Even if you haven't used this commas here, here in y, when it stores this, the comma comes automatically kind of. So next is you use this x plus y expression and store it in z. So this is the vector addition. So it will just add element by element. So it's simple. So let's run this line and see what happens. So you get 1 plus 2 equals to 3, 2 plus 4 equals 6, and so on. So next is you multiply every element of, say, this x vector by 2. So when you do that, it's just simple x times 2 that you have to do, and you notice that it's 2, 4, 6, 8, 10, so that's fine. Next, if you want to do element by element product of every element of, say, this x and y vectors, you cannot simply write an multiplication sign. Since you are doing it element by element, you have to put a dot here, so that's dot multiplication that you have to do. So when you do this, it's simple, like 1 times 2 is 2, 2 times 4 is 8, 3 times 6 is 18, and so on. This is 28 and this is 50. Division is again similar. You do this divisions using, say, scalar division. So it's every element being divided by -4. So if I write z here, so you get this answer. Then again you can divide this, say, x by x when you do this. So it's you kind of dividing one vector by another vector, but let's see what happens when you do that. So let's write z here, and you get 1 here. So you are not dividing it element by element here. You are not getting an output which is a vector. You are just getting a scalar output because you are dividing that vector kind of by itself. But when you do this element by element, let's see what you should get. So now if you write z here, you get all ones as all the elements of the vector. Then for raising this to, say, a power of 2 element by element, so it's like you take every element of x. You cannot just put this cap sign and just write 2. So you have to do this dot cap. So let's do that here again. So this z should be, all those x variables were 1, 2, 3, 4, 5. So here you are just raising everything to 2, and this is the result that you have got. Then you have the simple things like taking absolute values, square root, and those things. I'll just remove this semicolons and run those together. So anyway, it's pretty simple. So let's run this part. So for the first one, this absolute value is 5, then square root of 4 is 2, the ceiling of this 2.4 is 3, the floor of this 2.7 is 2. So it's simple. So now let's clear everything. Okay. Some issue with me. Okay, so I have cleared everything from my workspace and command window. So the next is the important part of this MATLAB, which is the matrix generation, matrix operations, and so on. So when you write a matrix, say A, then you have this 1, 2, 3. Then suppose you separate using this semicolon here. That means you have ended your first row, and these are your entries to your first row, and you need not have any commas there, but you can also put it, so that's not a problem. So you have 3 columns that you have representing, and then you can add as many number of rows as you want, but you need to have 3 columns. So you need to have some sort of a similarity from here to here, the number of elements that you have. So let's run this and see how this A matrix looks like. So when I type A here in my command window, you get this 1, 2, 3, 4, 5, 6, and 7, 8, 9. So this is row wise kind of initialization. You can take transpose by this A inverted comma that you have here. So it's simple. So if you run this, or A prime, that you can tell this. So this X is nothing but, now you have just everything flipped, and you have the transpose of the original matrix. Then there is other operations like ones and zeros that you need to know. So let's run this and see how A looks like now. When you write it as ones, 1, 4, that means you have all ones as an entry in your matrix, and 1 is the number of rows that you have, and 4 is the number of columns that you have. So this is a 1 cross 4 matrix. Similarly, if you do this for zeros, then every element should be zeros. So this every element is 0 here, and this is how your B matrix looks like. Now if you combine A and B, so and store it in C, let's see how C looks like. So it kinds of adds extra columns there. So this combination, it's along that row itself, and now you have a dimension of 1, comma 8 or 1 by 8. But if you put a semicolon there and then write B, that means you are saying that the row has ended there, and then you are starting the rows of B. So D will look something different. So if I now write D, so it's like first row was that all ones, and the second row, since you have put that semicolon, will be all zeros. Yeah, so this display function can also display this D, I think. Yeah, so that display D gives you that D variable itself, or D matrix itself. So, okay, so let's add another row. So this, let's run this line 31 and see what happens. So now when I write D, so it will add another row, the third row, and with all those elements being as 0. So this colon means all the elements are in that third row. And again, that display function can give you that entire D that you have right now. Then for identity matrix, you have this expression. So this I5. So if I run this, and maybe I'll just remove the semicolons here. It will be easier for you. And this one, yeah. So let's run line 33, and it will give you the identity matrix of 5 cross 5 dimension. But suppose you don't have a square matrix. Now when you write I, 3 and 4 and run this, what will happen is that it will generate a matrix which is of having number of rows as 3 and number of columns as 4, and all the diagonals will have an element 1. So you have only 3 diagonal elements in this case, and starting from the left top element, and then you can draw a diagonal, and all those elements have to be 1. Similarly, if all of these are zeros, so then let's do this. So all these are zeros. 1s, 3, 2 will give you a matrix of dimension 3 having rows 3 and columns 2 columns, and all those elements are 1. Then if you write diag x, so this x that you have right now is 147, 258 and 369. The diagonal elements of this x matrix is 1, 5 and 9. So if you just directly run this, what you will get is 1, 5 and 9. Next is rand 2, 3. So let's see what this function does. So let's run this. So it will generate a random matrix of dimension 2 cross 3, and so every time you run it, you will get different answers, and probably it generates a value between 0 and 1 itself. So that's fine. Then you can assign, say, y equals to x, so those kind of operations you can do. So this is fine. Then this is dot division. So this is element by element division that you can do. So let me remove this semicolons and see what happens. Now let's run this. Yeah, so this is element by element division, and since these two matrices are equal anyway, so you'll get all ones. Now you can do element by element multiplication as well. So this 1 is multiplied with 1 and you get 1, then 4 times 4 is 16, 7 times 7 is 49, and so on. This you have already seen. And then this is something different. This is not dot multiplication. This is just normal matrix multiplication that you can do using this multiplication sign. So for that you need to have the number of columns of x equals number of rows of y, so that you already know. Okay, so let's clear everything again and let's get into the function. So I've written z equals sq3. So what sq is the function that you have written at the end of this file. So here also you use that function keyword and you can write this output y, and then your arguments are x, and this is your function name. And this is the body of the function where you do the square by just multiplying x times, like x times x, and you get the answer. So it's pretty simple function that I have written, and you can run this and you should get a solution of 9. So z should be okay. I think there is some issue. Oh, okay, since I have to run the entire thing, I guess, because my function is at the end, so this part haven't been run yet. Okay, so probably how I can show it to you. Okay, yeah, so there is another thing. When you are writing one MATLAB code .m file, all your functions has to be at the end of that file. So you cannot put something in between and then write your other parts of the code. So that was giving some error as well. So I cannot just cut paste it and paste it there. So let's try to do this way. Probably. Okay, and let's run this portion entirely. Okay, I think, okay, so if I just put it in a different file and run, so that will run as it is. So I'll show it probably at the end, because anyway I'll be running the entire thing again maybe. Okay, so that was about functions. Let's see, quickly look at the loops that you have. So suppose you were writing this for, let's clear everything. Yeah, so this for 1 colon 7, and you are writing y equals I square, and then you are displaying y, and this end marks the end of that loop here. So let's run this. So it will run till, say, this 149 till 49. So this again, as you have seen in R, the 7 is included here, so it goes from 1 to 7, those I values, and you are just squaring it. You can do something similar using while loops here. So this is the part of the code for that, and you get similar results. Then there is this if conditions that you can do. So you can assign, say, x equals -5, and you are doing this if x is greater than equals to 0. You are displaying that the number is positive or 0, maybe it should be positive or 0. And for the next else part, you have the number as negative. So what you are doing is that you can run this entire part, and the number is negative here because you have put x equals to -5. So that's again simple. Let's look at more of how to write function expressions, because that will be helpful in your optimization problem that I'll be solving sometime later. So here again you can write your function equals this @ of x. So this is the argument of that function, and this is the x squared plus 54 by x. So this function you have seen before. And if you write f of 2, then it will give you the output or the function value at x equals to 2. So let's run this together and see what happens. So you get 31, which is 2 squared plus 54 by 2. So that's 4 plus 27. So that's fine. Then you can have different functions and different, so this semicolon has to be removed. So yeah, so you can do this. So this is again a function of one variable. Now you can have a function of two variables. You can write it as x comma y and do this kind of a scalar type notation, and you can check what is your value at 2. So it's 26, and you can again do the same thing using the vector notation, where you will just pass this one argument x. And this is something different from R. In R you use that square brackets, but now you have this first brackets here to represent x1, and this x of, say, first bracket of 1 kind of representing the first element of that vector x, and this represents the second element of that vector x. So this is x1 and this is x2, and it's pretty similar, so you should get the same answer 26 here as well. So let's see what you can get it or not. Yeah, I got it as 26. So let's close everything, and yeah, now it's all about plotting. So this ref line is the way of plotting your straight lines here in MATLAB. So in R, I think you had something like AB line, so that's something, it's the command is different here, and also the syntaxes and all are different. So you can have this my line 1 0.1. So this essentially gives you a straight line with, say, if your straight line equation is y equals to mx plus c, so your m is 1 and your c is 0.1. so that's exactly been written here in this legend, is that y equals 1 times x plus 0.1, and you can run this entire thing. So this grid on will show you the grid lines, then this is the equation of that line, then this is the color that you want to have for your line, and then you can have those font sizes and everything being adjusted. This is the color of the legend, and let's run this and see, and this is the placement of the text that you want to do. So let's run this and it will open up a plot window probably. Yeah, so the straight line is being represented using that red color. This blue color is for that legend, and where you need to place this text is kind of decided using the first two arguments of that text parameter. So that's how we can draw straight lines using ref line. So let's move on to the next one, which is again similar. So just clear everything, and again if you want to draw a straight line, say, let's draw this, I'll explain after that. Yeah, so this gives you a straight line parallel to the y-axis, so it's x equals to 0.5. so if you want to have some sort of a straight line like this, you can directly use this command x line. Now suppose you want to have y equals to 0.5, then what you will do, you'll just use y line and you will just place your legends accordingly, and you will get the final straight line plot. So that's all about straight lines. So let's move on to the function plots. So this is all about 2D line plot that I'll be doing. So suppose I have my x being defined from between, say, 0 to 20, or let's run this using this interval 0.01, and this is my function expression. So it kinds of takes all those points of x, and you are doing this dot division or dot power, because you are doing that for every element by element of that vector, and finally you can plot that. So let's, I think I haven't plotted for this one, but let's do it for the other function. So suppose my function is this one. Now let's plot this, and with the title and x levels and y levels. So let's quickly go this, and this will give you the 2D line plot. That's for the other function. So that's just not a line itself, it's a curve, so that you can get. Okay, so let's quickly get see some of the more things. So this linspace gives you, I think, around 50 points between 0 and 10, and again you can do some sort of a plotting. Say your function is sin x, and you can plot it, and suppose you want to plot other functions as well in that plot, so you can use that hold on command, and you can have different functions and you can plot it, and finally when you are done you can write it as hold off, and then just let me quickly show it to you. Yeah, so this gives you different plots on the same plots, and the last one was a scatter plot, so that's why it comes like this. Then I think I have a couple of more, then I'll go into the optimization part. So this is the contour plot. So again I have written the functions, and then I've defined the intervals, and then you can have the contour plot. Yeah, so this nice plots will come. And then finally, uh, last one was the surface plots kind of. So this one is the contour plot. So let's do this. Yeah, this is the contour plots with all those contour levels. And finally, I wanted to run this this function that you write. So that's an user defined function. So I don't know whether that will work in this file. So let's run the entire thing and see what happens at the end. Okay, so this has appeared. Okay, let me do one thing. Yeah, so that z is now 9. So that part has indeed run. So that's fine. So that's all about the basics of MATLAB. I don't think anyone will have any doubts related to this. So these were also covered in the class itself. So let's quickly move on to the optimization part, and then I'll be discussing the assignment part in the last 10 minutes. Okay, so for this optimization, so this will be doing single variable, multivariable optimization with unconstrained or constraint with constraints. So let's do this. So you have already seen this commands, so that's fine. The first I'll be doing is a single variable unconstrained optimization problem. The function I have already written. So this is how you write your function of one variable. This x1 and x2 gives you the lower bound and upper bound of that x variable that you are using. Then this options gives you this optim set. So this if you can use this and that will display your iterations, and the functions will be plotted, and also it calls this at this optim plot fl function. And the function that kinds of does this optimization is if min bound here. Since you are defining this bound here, you can search within that bound, and you are minimizing that function, and you are passing that objective function your lower bound, upper bound, and these are your options that you can set. And finally you can display your solution point and objective function. So let's run this and see what happens. Yes, so when you do this, you get a solution of, say, objective function value of 27, and your solution point is 3. So when you run this course, I think you might find issues with like the package is not installed or something. The optimization tool is not installed. So for that, what you have to do, you have to install it. So I think you can install from here itself. So you can go to home, then you can go to add-ons, then you can go to get add-ons, and then this will open up a window. Yeah, so whichever package you want to install, you just search it here, and then you will get an option to install that package, so you can install it. And also your MATLAB will close when you try to install it, so you have to save your work before you do this. And then when you restart your MATLAB, your package will already be installed, and you can run this this code using this function that I have used in this .m file. Okay, so moving on. So again, a single variable function, suppose I am using, so it's pretty similar to before. So suppose I have x1 equals 0 and x2 equals 5. So these are kind of my lower bounds and upper bound that I have. Now what I'm doing is that I want to suppose plot this function. So what I am doing, I'm generating points between my lower bound and upper bound at an interval of 0.01. So this x kind of stores those points, and then you can pass those points using this dot operators, and you can get to your function evaluations. And finally, what you can do, you can plot this x of f, those function at those x points. So let's do this and see how the plot looks like first, and then I'll go into the optimization part of this function. So let's do this. Let's run this part only. Yeah, so this is how the plot will look like. So this is evaluated at those points that you have generated. And the single variable optimization, it's again similar. So you can define your function, and again I'm using that fmin bound function, and between that x1 and x2 you can do this, and you can run this portion and you can finally get to your solution. So suppose I do this, yeah, so your solution point will be 2 and your objective is -16. So let's quickly look at another example. So this is again single variable unconstrained optimization. This is as before, so I'm not going into the detail of it because the code part is similar. It's just the function that is different. So I'll just quickly run the entire thing, and again it will get solutions like this. The solution point is 2.07. Okay, so let's get into the multivariable unconstrained optimization problem, where what you can do, you can define your objective function. So this is the function that you have already seen, and you can do some sort of a surface plot at first. Then what you can do, you can do this initial value that you can give. So this is 3,3. And then you can set the options that you want to use. And now since you are not putting any bounds here, so the function that you will be using is fmin search, and you will just pass the initialization point that you use, and you can use the options and you can get the solution. So this is also unconstrained optimization. It's just that you need to give an initial point, that's all. And the rest of the things are pretty similar. So first the surface plot will be generated, and then you get this steps of this optimization plot function. So after a few iterations it kind of converges, and the function value, current function value, is very close to 0, and the solution point is 3, 2, and you can also check the steps of, I think, okay, so that's not being displayed here, that's fine. So yeah, so that's how you can get this multivariable unconstrained problem, you can solve it. So there is another example with similar functions. Again, you provide some x0 and you can play around this different values of x0, you might get different solutions to that. So if you run this for this function, so again you will get 9.9 and the solution points is around this. Okay, so that's all about multivariable problems. I think we have already also seen this couple of examples in the R coding as well in that problem. So this is similar results that you are getting here as well. So this is again similar for another function. I think those were discussed in the class. So again we are getting a solution around 1 and 1. So let's move on to the constrained version of this problem. So that's more interesting. So I have, I think, 1, 2, 3 examples of that. So for that, what you have to do, you have to write a function separately to store those kind of constraints that you have. So for the first one, you can have different kinds of constraint. One is the linear constraint, another is non-linear constraints, and within linear constraints you might have inequality type constraints or equality type constraints, and within non-linear constraints as well you can have both equality or inequality type constraints. So what I have in this problem is that for non-linear constraints I have this 3 equality type constraints. So these are kind of equals to 0 that you have, and I have 5 variables here, so that's why this x1 to x5 comes into picture, and those 3 I have stored it in CEQ, but I don't have any inequality constraints for non-linear constraints, so I have to put that as an empty list. So that's exactly what I have done here in this function. And let's get back into this main part of this code, where you just put an objective function. So whatever expression is given, you put an initialization point, which is x0. These are your lower bounds and upper bounds of all the variables, and that's why I'm using ones to represent it compactly. So all the lower bounds are -5 and upper bounds are 5. then this is for just printing purposes of initial objective function value at that x naught. Then the linear constraints, you don't have any, so you don't have any equality constraints, or you don't have any inequality constraints as well, so you can just put it as empty lists. And this nonlinear constraints, you are calling it from the function that you have already defined, that I have shown, which is present at the end of this code. And again, you can optimize with this f min con, this function, where you have to pass the objective, the x naught, the a, b's, the a equality, b equality, lower bounds, upper bounds, and the non-linear part that you have defined, and this will finally give you the final objective and the solution point. So I think I have to comment the rest of the parts in order to run this, because that will cause an issue. So let's do this. I'll quickly comment the part. I think this is Control plus R you can use to comment here in, yeah, Control plus R to comment everything in MATLAB. Let's also comment whatever was there before, and so that I just run that part. So I think till here I can comment. Alright, so let's run this entire thing and see how the solution looks like. Yeah, so the solution point is minus 1.71, minus, it's plus 1.59 and plus 1.82 and so on, and the objective is 0.05. So I think this example is clear. So let's quickly get into a couple of more examples, and then I'll wrap it up with the assignment discussion briefly. So let's uncomment the rest of the parts, so that you can do using Control Shift plus R. And now let's comment this portion that I have already run. So let's quickly do this. Okay, so now for this function, you again have this time you have a function of two variables. You have the initial point defined, the lower bounds and upper bounds defined. Linear constraints are not present, and this different function is representing the nonlinear constraints right now, NL_1. So this is the part that I have written for that. So now what I have, my equality constraints are not present for nonlinear constraints. I only have inequality constraints. So these are less than equals to zeros, so that those two constraints I have put here. And let's run and check what you get, but for that I have to comment this part as well. Yeah, so let me comment this. Yeah, so we'll get a solution of 3.58 and minus 1.84. So for the last example, let me just quickly go through this, and since I'm okay. So here again, what I am doing, I have this function expression defined of two variables, and then I have this initial point minus 1 and minus 1. Then again what I have, it's I have nonlinear constraints. Since I don't have any linear constraint, I can directly put those empty lists here itself, and then I'll just call that non-lin con out the con function that I have here. So I don't have any equality things, it's only inequality constraints, so that I have put, and you can put it compactly using this semicolon. So this is for the first constraint, this is for the second constraint. And now we can run the entire thing, and you get a solution of minus 9.54 and 1.04. So that's how we can solve this classical optimization problem using MATLAB. So I still have some 5 minutes left. So any doubts related to this? Otherwise I'll quickly discuss this simple assignment tasks that you have this week. You can directly put it into MATLAB and you can get the answer, so that's not a problem. Okay, yeah, any doubts you can let me check. Okay, yeah, I think there is no doubt. Okay, so For the assignment problems, I think there are mostly theoretical questions this week, and I think you can answer that pretty easily if you go through the lectures thoroughly. There are not much numericals, or rather there is no numerical at all, I guess, in this week's assignment. So it's just some of the MATLAB codes are given and you are asked just to run that part and what will be the output of it. So that's essentially you have to do. So I've tweaked some of the values here and there, so don't just run this part of the code and write your answers, that will be wrong. So yeah, be careful with that. But anyway, let's discuss for the sake of completeness. So what I have given you a vector, say VCT. So this is for one problem where I have this bunch of elements stored in that vector, say 35, 46 and so on. So now I am asked you what is this VCT of 5. So this 5 means it's the fifth element of this vector. And remember, this indexing starts with 1 here. So when I ask you VCT of 1, that should give you an output of 35. 2 should give you 46. This should give you 78. So VCT of 5 should give you an output of 7. So let's see if I run this and you get the same answer or not. Yeah, so the answer is 7, so that's fine. So all I can do is clear variables. Yeah, so this is your VCT and this is the answer that I was looking for, which is 7. So that's fine. So next you are given that vector again, and now you are asked to evaluate this expression. So it's again pretty simple. You have some since you are dealing with just a single element, you can raise it to some power, and also you can add this SQRT of say VCT of 7 and so on. So let's run this and see what will be the output. Yeah, it should be 352 and something. So yeah, be careful with the expression that have been given, and you can just directly run this. So that's not an issue. Next is you are given this matrix. Suppose let me run this first line and write this. So this is your matrix 3, 12, 3, 5 and so on. What you are asked is what is the difference between this 2, 3 element. 2, 3 element means second row, third element, which is 10. And which is this 1, 2, which is the first row, second element. So this is 12. So 10 minus 12 should be minus 2, and minus 2 should be the answer. So let's see if we can get that. So these are pretty simple problems. So yeah, so your answer is minus 2. So that's again pretty simple. Okay, next is you are given a function expression, say e to the power x squared divided by square root of x cubed plus 5, and you are asked the value at x equals to 3. So again, it's a function of a single variable, so it's pretty simple expressions that you can directly evaluate, and this will be like 1432.4 or something. So that's the answer here. So again, it's simple. Next, you are probably given this matrix E. So let's do this. So you run E, and this is how E looks like. Now you have 2 rows. Suppose you add a third row where the element starts from 10 and it can go up until 22 and with an interval of 4. So it will have elements 10, 14, 18 and 22. So if you run this, now your E becomes, so this will be the third row of your E matrix. And now probably you are asked k equals to now I5. So what does k look like? So probably it doesn't have any relation with E itself. So one of the questions, so I think it's pretty simple, or just a simple tricky question. So when you write I5, you get an identity matrix of 5 cross 5. So that's about it, and probably you have 2 more problems. So let's discuss those quickly. You are given this x, suppose, then you can write it as, so you have from minus 3 to 2, you generate points at an interval of 0.01. So this is a vector of say having number of columns as 5 0 1s, And then what you have, you do some sort of an evaluation of functions at those points. So that's why this factorized operations are there, dot times this dot cap and so on. So you have these three expressions, y, yd and ydd, and you are plotting this separately with respect to say x. This y, yd and ydd are plotted. So when you do this, you get a plot like this, and now you are asked to get the maximum values of these functions between those points, and those you store it in z1, z2 and z3. So when you run this, you get an answer of z1 equals 35.46, z2 55 and z3 36. So that's pretty simple. Then you can do some sort of a pie chart plot as well. So suppose you are given some grades, which is say 11, 18, 27, 8 and 1. So what percentage of 100% have been like captured by those grades? So when you do this and you write this class grades, so the plot that you generate, I think it didn't appear, I guess. Should have appeared. Okay, I think this part, what is the issue? Earlier when I was running, you could see a pie chart, so plots, okay. Anyway, let's do this once more with a different. Okay, I think there is some issue with change that. Okay, I think just let me get to the assignment problem. Yeah, so the assignment problem is something like this. It should generate a plot, but I'm not sure why it is not being generated here. Okay, let me run the entire thing. Okay. And let me run the entire thing. Okay, for some reason it's not getting generated here, but I think when you run this, this should generate a plot. So since you have some pie of this, so it should generate a pie chart or something. So I don't know why it isn't appearing. It's not appearing anywhere else as well. Anyway, I'll try to, okay, I think I had that window open, so that's why that thing happened. So yeah, so that's how the chart will look like. So it will convert it into equivalent percentage, so that if you add all this percentage, they will add up to 100%, and that's how the chart will look like. So that's all about the assignment problems. It's pretty simple this week. I think I've already given you the kind of how to do this MATLAB problems. The others I think you can answer on your own. So if you have any doubt, you can ask me now. Otherwise, you can join the other session. So next week I'll be discussing the remaining portion. That will be the last class of this course, and in that I'll be, I think, discussing couple of problems using MATLAB and R. And also, if you have any more doubts before the exam, you can ask me in the next week's class. So so that will be the plan for next week. So that's all about today. And yeah, if you don't have any question, you can join the other session.